Welcome back. Today I will be talking to you about the cross product. And so to start out, let's just define the cross product. So I'm just going to start with a definition here. And the cross product can be defined this way, that we have a vector u crossed with a vector v is going to be equal to the magnitude of u times the magnitude of v times the sine of theta times the vector n, where n is a unit vector perpendicular to the plane containing u and v by the right-hand rule. Okay, so if you have two vectors, u and v, with the right-hand rule, if you take your right hand and start your fingers at u and move your fingers towards v with your right hand, which direction does your thumb face? Does it go up or does it go down? So if you think about that, your thumb would actually point down in that situation, and so you would get another vector that is perpendicular to both of these vectors in going downward. Okay. And it would have some length, and that length or magnitude is right here. That's the magnitude of u times the magnitude of v times sine of the angle theta, which is the angle between the two vectors that you started with. Okay, so that's how we define the cross product. Calculating it that way, not as easy, but let me talk to you about some things to know about cross products. So let's say that you have a vector u and you cross that with a vector, wanted that to be a vector v, and you cross that with a vector v. All right. Well, what you get out of that is a vector. Okay, this is going to be a vector. And that's already different than what we did in our last section about the dot product. If you dot two vectors together, you're going to get a scalar. If you cross two vectors together, you're going to get a vector. So in some sense, you kind of can think of there's two different types of multiplication for vectors. You can multiply two vectors together and get a scalar. We call that the dot product. And you can multiply two vectors together and get a vector. We call that the cross product. Okay, so if you take u dot v, then you get a scalar. All right. Now, if you took this vector u and dotted it with that perpendicular vector n that you get in the cross product, then that's always going to give you 0. Similarly, if you took v and you dotted it with n, that's also going to give you 0. And notice I didn't write 0 as a vector. That's the scalar 0. Why is that? Because N is described as being perpendicular, or another word for that is orthogonal, to both u and v. So since it's orthogonal to u and v, if you dot it together with u or v, you're going to end up with 0. Okay, so that normal vector N that you get out is going to dot together with both of those to give you 0. All right, here's an interesting question. What if you have that u crossed with v is equal to the 0 vector? Okay, so if you cross two vectors together and get the 0 vector, well, if u is the 0 vector or v is the 0 vector, this isn't super interesting. But let's say that they're not. Well, what is the cross of two things? Well, this is equal to magnitude of u times magnitude of v times sine of theta times all of that multiplied by some normal vector n, or some orthogonal vector. Now, how could this be the 0 vector? Well, if n is orthogonal in some way, then it is not the 0 vector. So that means that we're talking about the magnitude here is 0. Well, if u and v are both not 0, then that means that sine of theta must be 0. But if sine of theta is 0, then theta is 0, and these things are parallel. So if u cross v gives you the 0 vector, then u and v as vectors are parallel. So that's a nice little result of the cross product, is if you cross two vectors together and get 0, you know that the two vectors are parallel to each other. Okay, very good. So let me talk to you a little bit about some of the properties of the cross product. So I have some properties of the cross product. So first, if I take r times u, where r is a scalar, and I cross that with s times v, where s is a scalar, then that's the same as r times s times u cross v. In other words, I can move those scalars outside of the cross and cross the two vectors first, and then multiply by those scalars. 2. If I take u cross v plus w, then that's equal to u cross v plus u cross w. Now, all that this is saying is that cross products distribute over addition. 3, I have that v plus w crossed with u, it distributes the other way as well. This is v cross u plus w cross u. 4, I have that v cross u is equal to negative u cross v. Okay, so if you switch the order of u and v, you just add a negative. So they do not commute. If you switch the order, it actually adds a negative sign. And 5, if I have the 0 vector cross any vector u, then I end up with the 0 vector. Very good. Okay, so these are the properties that it's nice to know. Now I need to talk a little bit about a form of vectors that is going to be helpful to us, and that is putting a vector into component form using i's, j's, and k's. So we can think of it this way, that I, j, and k, let me draw some axes here. Let's say that I have my x-axis, my y-axis, and my z-axis, where this is a right angle right here. Sorry, right angle. So what I can do is, what if I go out just exactly 1 in the x direction, so this is 1, then the vector that points from the origin to 1 in the x direction, I'm going to have a name for that vector, and I'm going to call that vector I. Similar, let's say I go out 1 in the y direction, then I have a vector that points to 1 in the y direction, and I'm going to call that vector j. Similar, in the z direction, if I have a vector that points up 1 unit in the z direction, I'm going to call that vector k. All right, so if you have a vector u that I'm going to write, let's say 1, 2, 3 is kind of its standard component form. Another way that I could write that vector is it's 1i plus 2j's plus 3k's. And that would give me the same resulting vector. It's go 1 in the x direction, go 2 in the y direction, and then go 3 in the k direction, and then you get your vector u. Okay, so that gives you another way of writing a vector in its kind of component form using I, j's, and k's. But this is helpful when we're calculating cross products, because we know that when we cross two things, we get something that is a normal or orthogonal vector. And so, and we know that we're using the right-hand rule. So let me write a few things down for us. What if we wanted to take the vector I and cross it with the vector j? Okay, so I and j, I'm using a right-hand rule. So moving with my right hand from I to j, then my thumb would be pointing upward. So I know that the magnitude of I is 1, the magnitude of j is 1, sine of 90 degrees, or sine of pi over 2 is 1, so I just end up with k as my normal vector. So the direction it would be pointing is up using the right-hand rule, and so I cross j just gives me k. Okay, this happens for all of the different vectors. Let me write down the different relationships. We've got j times cross k is going to be equal to I, and k crossed with I is going to be equal to j. Now, it seems like we've kind of done everything, but remember, if I flip the two around, I actually get the negative. So if I cross j and I do not get k, I get negative k. And if I cross k and j, then I get negative I. And if I cross I with k, I get negative j. So you get this little relationship where I like to draw a little wheel. I have a j, I have a k, I have an I, and then you can draw in like little arrows here. So if you have, for example, k cross I gives you j, and I cross j gives you k. But if you go in the reverse order, you get a negative. So if you go I cross k, then you should get negative j. Okay, so if you can remember I, j, k in that order, if you follow the order, you get a positive vector. If you reverse the order, you get a negative vector. Okay, so that's going to be helpful for what we want to do next. All right, so let me erase real quick. Let's consider the following. Let's look at the magnitude of u cross v. Okay, so we already know what u cross v is, and now we're looking at the magnitude of that vector. So that's going to be the magnitude of u, magnitude of v. Then we're going to take the absolute value of sine of theta. Oops. Whoa. And then we are going to take the absolute value of this normal vector n. All right. Now, the absolute value of a normal vector n is really not that and this vector n right here, we know that that vector is a unit vector. So the magnitude of that unit vector is just 1. So you just end up with the magnitude of u, magnitude of v, times. Now, what about the magnitude of sine of theta? Well, depending on where the vectors fall, sine of theta is always going to be positive because you always measure the little angle, you never measure the big angle. So this is always a positive value because you're never going to measure the angle as being bigger than 90 degrees when two vectors fall. It will just, you'll measure the smaller angle. So it will always be 180 degrees or less. So sine is always positive in between 0 and 180 degrees. So this is a positive value. Okay, now let's look at something that's kind of fun. Let me draw. This is going to be a vector u. Here's a vector, let's call it v. And now what I want to do is let's draw a little parallelogram here. Okay, so I completed this parallelogram using u and v, and I'd like to know, so what is, let's say I have an angle between these two, theta, then what is the area of this parallelogram? Well, maybe you remember how to take the area of a parallelogram, maybe you do not, but what it is like if I cut off this triangle and moved it over here, then I would just have a rectangle. So I just have the length of the base vector times this height. Okay, so the length of vector v is the magnitude of v. So that's the magnitude of v. And then the height of this parallelogram is going to be the magnitude of vector u, which is right here, times sine of theta. So the height is magnitude u times sine of theta. But that's exactly what I have up here. So in other words, the area of that parallelogram is the magnitude of u cross v. So the magnitude of u cross v ends up being the area of the parallelogram formed by the vectors u and v. Okay, so if you know what your vector u is and you know what your vector v is, if you want to know the area of the parallelogram that's formed by those two vectors, you just take the cross product of u and v and then just take the magnitude, and that gives you the area of that parallelogram. Okay, that's kind of cool. All right, so now what I want to do is I want to show you how we actually go about finding a cross product in general. So what I'm going to do is let's just start with u cross v. All right. So u cross v can be written in its component forms using i's, j's, and k's. So let's do that. And so what I'm really doing here is I'm taking u1 times I plus u2 times j plus u3 times k, and I'm crossing that with v1 times I plus v2 times j plus v3 times k. All right, now let's distribute all this, because now we've just got the cross of a sum of vectors, and so we know that we can kind of distribute this, and so I want to distribute it. When I do, so I get u1 times I cross each of these guys. Okay, so let me rewrite. So I'm going to take this one and distribute it across this whole vector over here. So I get u1 times v1 times I cross I times I cross I. Okay, then I get plus u1 v2 times I cross j plus u1 v3 times I cross k. All right, so that's everything that has to do with u1I. Now I'm going to keep going for u2 times j and cross that with each of the three vectors over here. Okay, so plus u2 v1 times j cross I plus u2 v2 j cross j plus u2 v3 times j cross k plus, okay, now I'm going to do the same thing with u3 times k crossed with this entire vector. I'll distribute it, and I get u3 v1 k cross I plus u3 v2 k cross j plus u3 v3 k cross k. Now, what did I say about two vectors that were parallel to each other? What is their cross product? We remember earlier I said that the cross of two things that are parallel to each other is 0. So I and I certainly cross together to give you 0, because I is certainly parallel to itself. Same with j cross j, same with k cross k. So all three of these terms are just going to be 0. Okay? So if I rewrite this, I get 0. And then I get U1 V2 times I cross J. But I cross J we said was K. So I get plus U1 V2 times K. Now I get plus U1 V3 times I cross K. I cross K is going the other direction of the circle. Remember, it's I, J, K, and it moves in this order. So I times K gives me negative J. So this is minus J. Okay, plus U2 V1 times J cross I. J cross I is going the opposite direction, so I get negative K out of that. Then I get plus 0 for this term. Then the next term is U2 V3 times J times K, which is I, plus, then I get U3 V1 times K times I. K times I is going, K times I is going to be J. Okay, plus U3 V2 K cross J. K cross J is negative I. And finally, we have plus 0. All right, so now we can combine all these things together, and I can ask, well, how many I's do I have? How many J's do I have? How many K's do I have? Well, first let's look at the I terms, and there should be 2 of each. So here's an I term, and here's an I term. So really I have a U2 V3 minus a U3 V2 times I. Okay? Plus, I'm running out of space here, but what is the J term? So the J term would be, here's a J, and here's a J. So I have a U3 V1 minus a U1 V3 times J. And then what about the K terms? I have a K and a K. So I have plus U1 V2 minus U2 V1 all times K. And so that gives me my cross product in IJK form. Okay, all of that is just to show what you would get. But what's really nice about this actually is the same as a determinant. Now, it's the same as the determinant of a specific matrix that contains I, J, K, U1, U2, U3, and V1, V2, V3. Now, some of you have worked a little bit with matrices before and have maybe taken the determinant of a matrix before. But if you haven't, that's okay. I'm about to teach you how to do it. So I want to teach you 2 ways to take the determinant of this matrix. And the first way is that you could write the first 2 columns of this matrix over again. So let me write I, U1, V1, and J, U2, V2. Okay? And now what I call this is the method of diagonals. So the way that I want to take the determinant or cross U and V, it's equal to this determinant, and the way that I'm going to take this determinant is the following. I'm going to look at this first diagonal line, and I'm going to say, okay, that first diagonal line is U2 times V3 times I. Then I'm going to take the next diagonal line and multiply those together. So that's U3 V1 times J. Next diagonal line is plus U1 V2 times K. Now I'm going to reverse the diagonal lines and go the other direction, but now these are negative. So I'm going to subtract U2 V1 K. Now I'm going to subtract again minus U3 V2 I, and then subtract again U1 V3 J. And notice what that gives me if I combine the I's and the J's and the K's. Then I get U2 V3 minus U3 V2 I. And then I get plus U3 V1 minus U1 V3 J plus, and then the K's, I get U1 V2 minus U2 V1 K. All right, so that's one way to do it, is just taking these diagonals, 1 diagonal, 2 diagonals, 3 diagonals, 4, 5, 6. That's one way to take the determinant of a 3 by 3 matrix. Now let me show you one other way, and honestly this is the way that I like to do it because it's kind of easy for me, but if it's easier for you to do some other method of taking the determinant of the matrix, that's absolutely fine. Use whichever way makes the most sense to you. So let's say I have IJK, U1, U2, and U3, V1, V2, and V3. Then what I'm going to do is I call this the horseshoe method of taking determinants, and really it's the same thing as the diagonal method, I just think of it a little differently. And so what I do here is first I take this first diagonal, which I did before, and I get U2 V3 I. Then I take this horseshoe like this, and so I get plus U3 V1 J. Then I take the other horseshoe, which is U1 V2 K. Now I go the other direction. I go down this way, and all these are minus U2 V1 K. Then this horseshoe, which is minus U3 V2 I. And then finally this horseshoe, which is minus U1 V3 J. And that's what we call the horseshoe method. And if I combine the like vectors here, I would get the same thing as if I would have done the diagonal method of taking the determinant of that matrix. Okay, so be familiar with one of these two. Either way works. Typically, I'm going to use the horseshoe method just because I don't have to write those two columns out again. So now let's do a concrete example here so that we can see how this works in practice. So an example, let's find U cross V if the vector U is equal to 2I plus J plus K, and V is equal to negative 4I plus 3J plus K. All right, so I want to take the cross of those two vectors. So what I do is I set up a 3 by 3 matrix that I want to take the determinant of. So it's the determinant of, the first row is just I, j, k. So just fill that in every time. The second row is u, but you don't put in the i's and the j's of the k's, just the components themselves. So 2, 1, and 1, because there's a 1 right here, and there's a 1 right here. And then for the v vector, I've got -4, 3, and 1. Okay, so now that I've got the determinant to take the matrix to take the determinant of, now I just need to choose one of those methods, either the diagonal method or the horseshoe method, and go ahead and take the determinant. So let's do it. So I'm going to use the horseshoe method, so I'm going to start here. So I get 1 times 1 times I, so I. Then I go horseshoe here. I get -4 times 1 times j, which is -4j. Then I get the third horseshoe, which is right here. 2 times 3 times k is +6k. Now I go the opposite direction here. That's -4 times 1 times k, but these are all minus. So if you want to put minus and then put them in parentheses, then I get -4k. Then the second horseshoe is here, and that's 3i. And then the last horseshoe is right here, 1 times 2 times j plus 2j. Okay, so now I can distribute that negative, and I get 1i here, and then I get -3i's here, because I distribute this negative right here. And so I get 1i minus 3i's is -2i's. Then I get -4j minus 2j's, so that's -6j's. And then I get 6k's minus 4k's, so plus 4k's, which is 10k's. So the cross of u and v in this case is this vector -2i minus 6j plus 10k. All right, so that kind of shows us how to take the cross of two vectors. Let me give you another example. So, example, let's find a vector perpendicular to the plane of these 3 points. We'll call P the point 1, -1, 0. We'll have the point Q, which is 2, 1, -1. And we'll have the point R, which is -1, 1, 2. Okay, so we can't do this problem yet because we don't have any vectors in this plane. I'm sorry, on this Q, I meant to write -1. Okay, so this is the point 2, 1, -1. Very good. Okay, so what we're looking at is we have these 3 points, and we need 2 vectors to cross. And if I can cross 2 vectors, then I end up with a vector that is perpendicular to both of those vectors. Okay, so what I want to do is first let's figure out what is the vector connecting P and Q. Well, remember, if P, when I'm starting at P and going to Q as a vector, then I take the component of P of the Q and I subtract the component of the P. Okay, in other words, what I'm saying is that I take the first component of Q, which is 2, and I subtract the first component of P, which is 1, and that's an I, plus second component of q, which is 1, minus the second component, which is minus 1. That's j. And then, let me erase this over here, plus, now the k component is negative 1 minus 0, k. In other words, this is going to be I, and then 1 minus minus 1 is plus 2j, and then minus k. So that is the vector pq. Now let's figure out the vector pr. Okay? So the vector pr, same thing. I'm going to start with what's in r. Here, I'll erase these real quick. So I start with the first component of r, minus 1, minus the first component of p, 1, I, plus second component of r, 1 minus 1, j, and then I get plus 2 minus 0, k. So what do I end up with? I get minus 1 is negative 2i, 1 minus minus 1 is plus 2j, and then plus 2 minus 0 is 2k. All right, so I have my vector pq and I have my vector pr. Both of those lie in one plane, and I want to figure out what is a perpendicular vector to both of those vectors. Notice that if I have two vectors, let's say that this is p, and this is q, and this is r, then those two vectors lie in some plane, right? And I want a vector that comes out of that at a 90-degree angle both to PQ and PR. If I did that, then that's going to be a vector that is perpendicular to that entire plane. So what we know is if I cross two vectors, I get out a vector that is perpendicular to both of those vectors, and in this case, to the plane. So if I can cross PQ and PR, I'll get another vector that's perpendicular to that plane. So let's do it. Okay, so I want to cross PQ with PR. In other words, I write in my I, my J, and my K. And now let's remember what was PQ. It was 1, 2, minus 1. 1, 2, minus 1. PR was negative 2, 2, 2. Negative 2, 2, 2. So now let's cross those two vectors and see what we get. Again, I'm going to use the horseshoe method of calculating this determinant. I go this way and I get 4i. I go this way and I get 2j. I go this way and I get 2k. Minus, now go the other way, and I get minus 4k. Go this way and I get minus 2i. Go this way and I get 2 times 1 times j plus 2j. Minus minus 2 is 6 i's. Then I get 2j's minus 2j's, which is 0 j's. And then I get 2k minus minus 4k, which is 6k. Or in other words, I could just write 6i plus 6k. And this vector will be perpendicular to the plane in which PQ and PR both lived. So that's my answer, is 6i plus 6k. Very good. Okay, let's do another example. So for my last example, let's find the area of the triangle formed by the 3 points in the last example. Now, we could just use some geometry to do this, but we can make life a little simpler because we know something about the parallelogram formed by those two vectors. I already have told you that PQ cross PR's magnitude is the area of a parallelogram. So the area of the parallelogram is going to be the magnitude of 6i plus 6k. But that magnitude is just equal to the square root of this first component squared, 6 squared, plus this second component squared, 6 squared. So that is what? The square root of 36 plus 36, which is 72, which I could write as, let's see, 36 comes out of that, so this would be 6 times the square root of 2. Okay, so that is the area of the parallelogram. Now, that's not what I want. I want the area in the triangle, but a triangle is exactly half of the parallelogram, because if I have two vectors here and I form the parallelogram and I find this area, then if I wanted the area of just the triangle formed by those 3 points, it's just exactly half of the parallelogram. So the area of the triangle would be equal to 6 divided by the square, 6 times the square root of 2 divided by 2, or just 3 square root 2. And that would give me the area of the triangle formed by those 3 points. So that's kind of cool. So if you take the cross product of those two guys, not only does it give you this orthogonal vector to a plane, you can also use the magnitude to figure out the area inside of those 3 points. So all of those are very cool applications of the cross product, and they will be very helpful as we go forward. You're now ready to do some homework over cross products.